welcome to another class at educator.com in intermediate C++. Now, we've seen functions in the introduction class. You should be familiar with functions from whatever other language you've been taking, but we're going to get a little bit more detail into C++ specifics in the functions, a little more things about functions in general. So we're going to discuss a few more things. One of the cute things that we get from C is being able to put parameters on the main function, because of course we're going back a long time ago before we had Windows and X Windows and all these other wonderful things, GUI applications. You typed your things at the command line, and if you wanted the program to do something different, you put an argument on the command line to the program. So we're going to talk about a few things with that, with some typical types of parameters that you'll give to a main function as a dash help. Tell me how to do what you do. And we'll deal with inline functions, which is a C++ peculiarity to functions. Recursive functions, which most languages that have functions can handle. We'll take a look at doing that in C++. Something that's distinct to C and C++ is being able to pass a pointer to a function as a parameter, so that function you can have a caller call a program written by somebody else, and then pass that person a pointer to your function, so that person then can call your function. It's called a callback frequently. And we'll now teach you how to do that to the caller, but it's like you are the caller, and where somebody is calling you and then giving you a function. It's here when you're finished, call this function. And so how do you dereference a function pointer? And finally, we'll deal with some issues with passing multi-dimensional arrays into a function. Because basically, you pass a one-dimensional array. You can pass more than one, but then you have to put a hard-coded dimensions on the extra dimensions, and that can cause heartburn in a lot of applications. So there's ways of getting around those issues, which we will talk about in this class. So the parameters for main is our very first function. Your hello world was inside a main function. So we've always had int, which is a return value. Like every function has to have a return value. So who does it return to? It returns to the operating system that called the application. You have your main and your list of parameters, which so far we haven't given it a list of parameters. And then you have your code. And usually, not always, not every compiler will enforce this, but you should have a return that returns a value to the caller, which would be, in this particular case, would be the operating system. So the main function in C++, you would say, is overloaded. Now, you could do this in C, and they didn't call it overloading then, but now in C++, it would be something we'd call it a polymorphism. You're overloading the function call. So you've got these three different types of prototypes. You've got, or four actually, because you can have no prototypes. So you've got 1, 2, 3, 4 different ways of calling the main function. With int, all you get is how many arguments there are. So maybe you want to do something differently because there is an argument, or do something differently because there are two arguments. On one example, there's a program on most Unix systems called who. You type who and enter, it gives you a list of everybody who's logged into the machine right now. Now you can say who am I, and it will just give you your login ID. Well, as it turns out, the original program, all it did was say how many arguments are there. If I have two arguments, I'll just print out the one name. So you could say who are you, and it would still print out your list of names, because all it did was count the arguments. It didn't care what the arguments were, just that there were two of them. But most of the time, you want to actually see what the arguments are. So you have count how many, and then you'll have an argument list that's passed into the main function. There's also, it's not used very often, but you can get an environment list. You have the parameter list and an environment list. And those are external environment variables that are part of the operating system that define different things, like where to find functions, where to find libraries, what type of system you're in, whether you're in a shell, whether you're in a Bourne shell or C shell, etc. All these things would be given in a list of variables that will say like A equals some value, and then the next one will be like B equals some value. And these will all be external to the program. And in the operating system, you can put in there A equals 7 and run your program. That'll be in your environment list, A equals 7. But the way we'll see most of the time will be the second one, where you have the argument count and the argument vector. And you'll just have an array of character arrays. So here we're just printing them out. We'll say C out the argument list. We'll say this is my argument list, and then the integer arg_i, which is just something I put in there between arg_i and argc, incrementing arg_i, of course, and we'll print out arg, and then print out arg_i. This is the 0th, the 1st, the 2nd, and then argvec, and then end the line, and then we'll return to the OS. So it'll print argument list and say arg, and for each argument that you happen to put on the command line, it will print them out right here. And that's all this function does. There's some typical parameters that you would use for this sort of thing in a command line environment. I highly recommend always having a -h, so it gives some kind of help, so that when the user runs the program, he gets reminded of what the arguments are, what they mean. Typically, -v will mean the version of this particular program. So I've got version 1.5.6. I should get 1.7 because that fixes some bugs and whatever else. Or sometimes that may mean verbose. Depends on the application. None of these things are hard-coded or locked in stone. Different applications can have different things with different meanings. Just a -h, please make -h always be help. $U can be like the username who wants to log into some process, log into a database, whatever it happens to be. And of course, if you use a username, you'll need a password for that particular. But very often, it will also be the port for internet working connections. And sometimes they'll use lowercase p for that. There are some systems where some of the applications use capital P, some of the applications use lower p, because capital P was used for something else. So it depends on your application. And -f is very typically used. This is like my file. And it can be either the file that we're going to work with, like we need to compress this file, or we need to process this file, we need to extract data from this file, or it might be a file where more parameters can be gotten. Let's face it, with a dash and a letter, you don't have a lot of options, and some applications have got dozens, hundreds of different options. So rather than using the command line, you just tell it, this is my file that has got all of my different parameters set. It's also common now to have hyphen, hyphen, and a longer. It's no longer restricted to just a dash and a single letter. You'll have two dashes, which indicates I have a longer option name, and then a longer option name. So instead of dash V, you'll have dash dash version. Instead of dash capital U, you'll have dash dash user, etc., etc. Now here's a quick example of code. We've got our main. Of course, up here we will have IOStream included. And you're using the namespace, etc., etc. You put your preface comment block that says who it belongs to. And so if this argc is less than or equal to 1, actually it can't be less than, it will always be at least 1, because the 1, if there's exactly 1, that is the command itself. So if it's 1, that means they didn't put any arguments on it. So in this particular example, we want to have at least 2 arguments, and those 2 arguments are dash f and the file that we're going to process. There are also a couple optional arguments. So what we're doing here is, if we only have 1, that means no arguments were given, so we'll print out a usage. This is incorrect. This is how you use me. It's the same thing as typing with a dash h, if you program it that way, of course. So we'll print out the usage. We'll say usage. Now arg0 is the command, and then we're saying dash h is optional, dash v is optional. It's just a tradition that if it's inside square brackets, that means this is an optional parameter. And if it's not inside square brackets, that means you have to provide it. And if you don't provide it, you'll get some type of error message. And then in this particular case, we're returning a 2 back to the operating system that tells the operating system that we are not ending successfully. So if it's greater than 1, that means we've got some parameters. Now let's process all those parameters. So actually, you shouldn't need to start from 0. Let's start from 1. Because 0, like I said, is the command itself. So we're setting that particular argument, which is a character array, we're setting it to a string. So if that string is dash h, oh, they're giving us a dash h. They want some help. Let's print our page of help, including our usage, maybe a little bit of description. Dash h means help. Dash v means verbose or version or whatever it's going to mean for you. Dash f means, the next file. This is the name of a file where we need to get some more information, or we're going to operate on whatever we're going to do. So if it's not dash h, then we'll go else. If it's dash v, in this case, we're printing the version number, and then we'll exit. That's all we want to do is give you the version number. You can put all these parameters on the command line, but we're going to exit as soon as we get one that says what we need to do. We're going to do it and then go. That's the way this happens to be programmed. You don't have to program it that way. If it's dash f, now we have a file option. So that means the next parameter, so arg_i plus 1, needs to be the file. So we'll pass that file onto a function, which will do its processing and do what it needs to do, and then we'll exit. Now, one thing that's not here that you probably need to do is a test to make sure that argc is actually large enough to include arg_i plus 1, because it's very, you'll see people do app and then dash f. So, oh, there's a dash f. Let me get the next parameter. Well, there is no next parameter. So that means your application crashes. So you put a little test there. So we tested for dash h, tested for dash v, tested for dash f. There are no other options that we could test for, so we have an else, and we'll print an error message. The bad parameter, they probably put a dash x or something like that, whatever they did. So we'll print our usage, says, no, these are what our arguments are, and then exit. So some things to note. The very first item in the argument vector array is the program file, however it was run. So if you run it with this, to get to the full path to get to it, arg0 will be path my command. If you just type my command, and it happens to be on the path, and the operating system goes and looks down its path and finds it, it will pick it up and run the program. Your arg0 will just be my command, whatever it is you happen to type. Now, if you have multiple words that you want to be on a single argument, you have to put them in double quotes when you run the application. So for example, you have my command dash m message. This is your message in double quotes, and then dash t means whatever it means. So this is R2 because it's in quotes. So you have 0, 1, 2, 3. If you don't put those quotes in there when you type the command, you have 0, 1, 2, 3, 4, 5, 6, which may or may not operate. Some applications will operate that way. What they'll do is they'll just keep taking parameters until they get another one that starts with a hyphen, and they'll just concatenate them all together on your behalf. But if you're going to do something like this, warn your users, whatever, you put quotes around it if you're going to do that. And the argument, it can be operating system dependent. For example, we have g*glob*.txt. Unix and Linux variants will expand the wildcard into each matching file in that directory. For example, if we have global glob23.txt is one of the files, that file will be passed into my command. If there are several command files like that, like for example, let's suppose there's another one that, let's say it's 24. That will also expand. So you've got 23 and 24. It will grab both of them and pass both of those. You'll have arg1 will be the 23 and R2 will be the 24. That's the way that Unix works. Windows doesn't do that. So it's one thing that you keep in mind. If you want your file arguments to have an asterisk in it or a question mark as the other wildcard, which matches one letter, it won't work very well on a Unix system. So try to avoid those types of special characters. A return of 0 is passed back to the operating system, usually means success. You can have a shell script that runs several commands one after another, and it will test the return status. If it's something greater than 0, oh, we have an error. There's no sense in proceeding to the next command. So that's a positive integer means something is wrong. You cannot have a negative integer. There's some more things of note. The arguments are passed as character arrays. They're not string objects. If you want a string object, you just take the character array and copy it into a string object. It's also customary to have a both standalone argument as an option and as an argument that has a parameter, and you have to write your code to process it that way. The examples -h and -v are standalone. You put a -h, that's all you need. Hey, I want help, so you produce the help. -v, hey, I just want to know what version this program is. So, okay, you just print out the version. Something like -u usually means there'll be another argument. That'll be the user. So when you get the -U, well, let me see the next argument, and that'll be the username, and I'll say that as my user.name data and proceed on to continue processing the command line. And you also, of course, have to test, is there actually is another argument in there? If they have -U is the last thing on the command line, and if you just go ahead and try to process the phantom non-existing next parameter, your application will crash. Now, there is sometimes some confusion as to whether or not to put a space between the option and its argument. For example, here we have -U and there's a little space in there. So that's two arguments. You have -U and then you have user. There's two arguments next to each other. Some applications want no space in between. That's exactly one argument. You have to look at the first two characters, -U, and the rest of it becomes the argument to that particular option. Many applications, they don't care. They'll program it. It'll work either way. So it depends on what application what you need to write for your application. But remember, in some of the applications that you'll run, they'll want it one way or the other, and it won't work the other way. So the first way, when there's a space in there, you've got argv of n is your option. n+1 is the argument to that option. The other way is just one option. You have to look at the first two letters to determine, is this -U for the user, -P for the password, and then the rest of it's the actual argument. Now, other functions we need to look at are inline functions. You put the inline keyword, that tells the compiler to insert the body of this function explicitly into the code, but otherwise works just like a function. So it gives you function modularity without the function overhead. Normally a function means, okay, we process the parameters, we process where we are now, let's go grab the function location, jump to the function does its thing. When it's finished, we jump back to where we left off and then proceed with the rest of our processing. With the function, inline function, the function is just dropped right there in the code, right at that place. And as many times as you call it, if you call it 7 times in your code, you'll have 7 copies of your inline function dropped into your code. Now, that makes your code a little bit bigger, but you don't have to jump off to a function and jump back. So that gives you a little bit of performance gain. Not a great deal of performance. You really have to be running on a very, very, very tight schedule to bother with this. But there are applications where that's necessary, like game processing. When the character pulls his trigger, you want that bullet to fly out right now, not 2 milliseconds from now. Device drivers, you'll need that extra time savings. So it's another tool for that you can optimize your speed. So here's an example. Here we have a double with cube +1, double x. And what it does is return x multiplied by x multiplied by x, and it adds 1 to it. Cube +1. So here we have pressure at supersonic 56.9, just some arbitrary value I picked out of my head. And we're outputting the cube +1 of pressure at supersonic. So what it will do, it will act like this was an actual function call. But what we'll actually do is calculate x plus x plus x plus 1 and place that right there at that particular location. Our second time, we've got some other calculations, 17.0 plus q +1 of whatever else you might want to put in there. You might want to put to q +1 of 15 plus the pressure at supersonic. So the compiler will add those together, then pass it into the function, and the function is right there at that particular location. And note, the compiler does not guarantee it will make your function inline. It might choose to optimize it some different way depending on what the size of your function is. But this is basically your request to the compiler, take this code and drop it where I use it. Now, recursive functions is something that's not unique to C++, but something we need to talk about. Now, some algorithms are more easily understood in a recursive form. The basic definition is a function or algorithm that uses itself to solve a problem. C, recursive. So now we know the answer to that. So it calls itself to resolve a piece of the problem. The recursive call may be able to resolve its piece, or it may call itself again to get an even smaller piece. Some common mistakes is failing to handle the easy condition. So we get a condition, we don't need to call ourselves recursively, so just calculate it and return it. Another error people make is failing to do a smaller part. Every time you call yourself recursively, the recursive call should be a smaller piece. It should be closer to the goal. It should be less work to do each time. Because otherwise, in either of these cases, if you make the mistake, you might find yourself with a recursive infinite loop, and you want to avoid those, of course. So here's our classic example, is factorial. In case you're not familiar with math at all, factorial is like the factorial of 5 is 1 times 2 times 3 times 4 times 5. There's a very obvious iterative way of calculating. So for I equals 1 to your number, keep multiplying them until you get the answer. The recursive way is to define it recursively. The factorial for n equals 0 is defined as 1. That's your simple case, your easy case. Your complex case is to say that n factorial for a non-negative integer is n multiplied by the factorial of n minus 1. So now you've got a simpler issue. So solve the simpler issue and then multiply by that and then return that to your caller. So if you called yourself recursively, then you'll break it down smaller again, break it down smaller again, until eventually you get to the simplest case, have a result, and return those back up to your calling chain so you get to the answer. So for example, we have 4 factorial. 4 factorial is 4 times 3 factorial. Simple, except what's 3 factorial? Well, 3 factorial is 3 times 2 factorial. Great, what's 2 factorial? 2 factorial, 2 times 1 factorial. 1 factorial, 1 times 0 factorial. Aha, now we know the answer. 0 factorial is 1. So we reply back, reply back, reply back, reply back, and so we come up with our answer. It's 24. We can ask again. What's 5 factorial? That's 4 times 4 factorial, so that's 5 times 24, which is 120. So here's the code. Here's the code to do that. We have recursive factorial, we'll pass it in a long integer. If we try to do a factorial of a negative number, we'll throw an exception because it's not defined for negatives. If it's equal to 0, we'll return 1. Because 0 is our simple answer. The factorial of 0 is 1. We'll just return 1. Otherwise, let's return n multiplied by call ourselves recursively with n minus 1. The iterative reversion you may have seen. Same thing, throw our exception. We start off with our result, and for I equals 1 until we get to n, the result equals result times the integer, and return the result. Either way may seem equally useful, but just remember that there are some algorithms that are more easily expressed recursively, such as, for example, binary tree. Binary tree is basically a node with 2 binary trees attached. So we have a node with 2 binary trees attached. Now, a node might be null, in which case there's no binary tree attached. So it's either null or another binary tree. And since that's the definition, it becomes immediately obvious that any type of algorithm that you want to use to recurse, to search through the binary tree should be recursive. It's like, are you the number I'm looking for? No. Well, look in your first binary tree and ask him. If he doesn't find it, ask your second binary tree and ask him. One of these guys will come up with the right answer, particularly if it's something like, you've got, this is everything on this tree is less than I am, and everything in this tree is greater than I am. So now you've got a recursive algorithm that does a very fast search. So if this is like 200, this will be like 100, this will be like 50, etc., whatever it happens to be. And you're looking for 150. 150 is less than that, go down there. It's greater than that, go down there, etc., until you actually find it. So it's a perfect recursive algorithm. Now, our next thing is pointers to functions. You can have a function and pass a pointer to a function to the function. You'll see that awful in GUI programming. What you'll do is you'll get a whole set of application functions, API, and things that you can call. I want to paint a panel. I want to paint a label. I want to paint a field that a user can type into. I want to paint a button. And when the user clicks on the field, they can enter into it and tell me what they entered. And then we have the button. The user clicks on that. Tell me that the user has clicked that button. So what do you want me to do? Well, here's a function. When the user clicks that button, call this function. And that function will do something that's pertinent to the application. So the caller of a package passes a pointer to the function, and the package, when it needs to, will call the caller's function by dereferencing that pointer, and then call the user back, call the caller back. That's why it's usually called a callback. So example with a GUI package, let's say you have an add button. So you have a function here. This is your function that adds data into a database. And here's your GUI code where you call the GUI application and you say, paint me a button, paint it at this position, paint it this size, put this text on the button, and when the user clicks that button, call this function. And that will be my function, which takes the event info, it does something with it if necessary, or just grab whatever data I have and add it into the database. Now, you might be on the other side of that. You want to define a parameter to your function so that your caller can pass you a function, and then when you get to the particular conditions, you can call your caller's function. This is the syntax for that. So here's your outer function. Of course, you have a return type. Every function has a return type. This is the name of your outer function. Of course, you have your open parentheses. And then you can have as many parameters in here as you want, int, a, float, b, whatever. And then here is your function parameter. It has a return type. An open parentheses and asterisk indicates that it's a function, a pointer to a function, the name of your parameter, which will be the function that you will dereference, and then close that parentheses. And then I wish I had more room to put all this on one line. Then you'll have the parameters of that function, and then any other additional parameters you want to put in there for your outer function. So your caller doesn't have to really worry too much about the syntax. All they have to do is create a function, and if you need it for it to be an int, then define it to be int. And if you need to have one double parameter, and you put on here double p, then they have to put in their function double q, or whatever they want to call it. And all they have to do is pass that function in a parameter to your function. you're the one that has to worry about the syntax. Which, okay, the function is passed to you. Here's how you call it. You dereference that with the function dereferences, and then pass in whatever parameters that you've defined are necessary, and pass them to call the caller's function. Now, if like you need a double and the caller passes you an int, like if they define this to be int instead of double, the compiler will catch that and call it as an error. So you define it the way you want it to be. You publish it so that your callers know what it is, and then they have to follow those rules. So here's an example. We have a create button with an integer callback that has a return for event info object, which you've defined somewhere. So this is your function here. Someone else will create a function. They'll call it whatever they want to call it, have it given an event info parameter, and then they'll call you with that parameter. And so if you're some event that you have, whatever it is, and you just repaint the screen, you take the word on your button and push it down a little bit, like that makes it look like it went down when you click it, and then you call the caller's function to pass the information to them. That here's your information you want when the user pushed the button, do something with it, and then they come back, and then if there's a return value, you capture the return value. Now, one other thing we need to cover with functions is passing in multi-dimensional array parameters. The biggest issue in C++ of passing in a multi-dimensional parameter is really you can't do it. Arrays are all one-dimensional. There's just some conveniences of allowing you to pretend it's multi-dimensional. For example, if you call it like this, you will get a compiler error message. So the function receives a pointer to the array, but it cannot know the size of the information. That you have to hard code each dimension. So you can call this with A, and then have 10 rows and 15 columns. That will work. But then, well, what if I don't need that many rows? What if I need more rows? Well, you're kind of stuck. This is the way the position is calculated. So, for example, if we define an array, a two-dimensional array, size 1, size 2, now I want to, we have an array like this, and it's some particular size. We want to get to this particular cell. Well, it's actually a one-dimensional array where this bottom piece will be here, and then this piece next to it is there, etc., on up. It's got to calculate from here to get to where that particular spot is located. So it will take the position P1 and P2 and do P1 times 2 plus P2 to get to the actual address where that position in your array is located. And here's a little more complicated one for a cube, where you've got a two-dimensional array with rows, and put the rows here and columns there, and then a plane. So this is a three-dimensional array with columns and rows, and here's a third plane with columns and rows. So this is P. This is P0, P1, and P2, or P equals 0 rather. And you can have as many as you want. And there's etc. for each additional dimension. You have a 4-dimensional, 5, 6, which is, I can't think of any immediate applications, but physics thinks the universe is made out of 11 dimensions right now. That's their problem. So there's different ways of handling it. We can have a one-dimensional array, because it's passed in as a one-dimensional array anyhow, and pass in dimensions with the array and do your own arithmetic. It's a good use for an inline function. You can put in your locations and your maximums, and the maximums can be computed at runtime, and the inline function can just do the arithmetic for you. So here we have an example. We have an inline for a three-dimensional. So we've got the plane, the row, and the column, the maximum planes, the maximum rows, and the maximum columns. And what we do is return how to calculate a given position in our one-dimensional array. So when we call our function, we pass in a pointer to our one-dimensional array, and we pass in the maximum, the max planes, the max rows, and the max columns. And here we have our 3 loops, so we can go from each plane, 0, 1, 2, 3 for each plane. And then once we get to each plane, calculate each row. And then finally, each column, until as we get our position, using an inline function to do that arithmetic, to simulate having a 3-dimensional array. Now, other ways of doing it is to pass in internal data with the array. It's not the best solution, but sometimes it's the only solution, depending on what you're doing. Like, for example, here we have an integer, and the maximum for the integer is 200. So we'll define our array as being max plus 1, so it's 201. And the 0th position is where we will store how large that array is. So we call a function. We just have to pass it in the array. The function can inspect the 0th position and say, oh, okay, there are X number of elements in this array, and it knows to go from 1 to whatever the value in 0 is, in the 0th position. You have a 2-dimensional array of max rows and max columns. And the beauty of this, you don't have to do this as a hard code the way I've done it. This could be calculated in your processes. So we've calculated we need to have this many rows and this many columns. So therefore, we will allocate a 2-dimensional array to have that many rows. And for each of those arrays, we will set the 0th element. No, first we have to calculate the new. We have here an array of arrays, basically. So your first array is a pointer to the secondary array. So we're allocating that space and setting its 0th element to how many there are. So this is the 0th element of that, which will be, in this case, will be 100. So there'll be 100 guys over here. We'll put 100 there. And the other direction was 200. And so we'll go down each one of those. So we're getting a new array, which is 100 in each case, et cetera, et cetera. So we're simulating a two-dimensional array with an array of one-dimensional arrays, which is pretty much the way it works. But what we're adding here is we're allocating one cell in each case to say how long that array is. Now, extract that to 3 dimensionals. So you'll have an array of arrays, and each of those arrays is another array, and you can just go on and on. And now this may seem like a lot of hard work to do something, but sometimes it's the best way to do something. In particular, you've got an array of arrays, they aren't always the same length. So this one could be pointing to an array that's only got 2 elements in it. So that would have a 2 in there. And so, like, if your maximum array, for example, could be thousands and thousands of rows, but most of them have only got dozens of rows. So instead of having a matrix where it's a few hundred this way and a few thousand this way and having all of this space, most of which is empty, you can have the one that's that large actually take up that much space, and whereas others are much smaller. So for each particular spot, you allocate however much space that array needs, and then you put in the very first position how much space has been allocated for that specific array. So, and the beauty of it, now when you call your function, the function looks at the first one and says, how many arrays have I got? And then for each array it has to process, it looks at the first element of that one to see how many columns there are to be processed. Now, probably my favorite way of doing this is using objects. The object itself can have all the information necessary. So here we have a class called Array3D. We've got a pointer that's going to store basically a one-dimensional array that's going to have all the data. We're going to store what the maximum is, the maximum plane, the maximum rows, the maximum columns. It will have a whole bunch of other public methods that are necessary, so we need to get that information out to use it. So we have what we call it. We construct it with P, R, and Q with planes, rows, and columns, and initialize the maximum planes to what was passed in our constructor. Max P, max R, and max C. So when this code, and allocate the memory. So our array will become a new integer where the total size is maximum planes times the maximum rows times the maximum columns. So now we've got a cube allocated in memory as this object. We're represented as a single array, and we could do that calculation, which I hope you remember the formula because I'm not going back to that page. You can also test ranges. So if someone attempts to access, if this is a 3 by 3 by 3, if someone tries to access 5, you can throw an exception or do whatever else is required. So here we have an example. We're going to construct a 3-dimensional array with 3 planes, 4 rows, 5 columns, and we're going to call a function. And the function is just going to do a loop around the rows. So it will get the maximum number of rows. Like I said, we need to have additional methods more than what I displayed here. And so we go row equals 0 to the maximum number of rows and do the arithmetic that we need. So we're going to access the P and C were computed someplace else, and we're going to set these elements in that row to 17. And that's because of overloading the open parentheses operator. And the reason why we had to use the parentheses operator, you can't do multi-dimensional array operators as an overloaded operator. C++ won't let you do that, which is kind of a shame. So we use the open parentheses and treat it as if it was kind of a function. But that will work that way. And this is the Bureau of we don't get help here because we never implemented -H. Our programmers were too lazy. Please implement -H, document your stuff, etc., etc. And that's the end of this lesson for Intermediate C++, educator.com. I'll see you at the next lesson.